Hello. In this video, we will be discussing the solutions of IBHL Chemistry Paper 2, and this is of time zone 1. So let's start with the first question. In the first question, it's given as a statement that iron may be extracted from iron to sulfide, that's FAS. The first question says, outline why metals like iron can conduct electricity. So what could be the answer to this question? So iron is basically a metal. So what happens is it has a sea of electrons in its metallic structure. So these electrons are basically mobile in nature. So they can move, and as a result, it can conduct electricity. So we can frame the answer in this way. Iron, being a metal, has a sea of electrons in its metallic structure. These electrons, being mobile in nature, can conduct electricity. That's the answer to the first part of this question. Now the second part is justify why sulfur is classified as a non-metal by giving two of its chemical properties. Now our first property is sulfur generally forms covalent bonds with other atoms. Like we know the property of non-metals are to form covalent bonds. Okay. The second property, we can say that the oxides of sulfur are acidic in nature. So this is also true because not any of the non-metallic oxides would be acidic in nature. So using these two properties of sulfur, we can say that it is a non-metal. So we are done with the part B2. Moving on to part C, we have to sketch the first 8 successive ionization energies of sulfur. So sulfur has a total of 16 electrons, and so it has 6 electrons in its valence shell. So here we have to remove 8 electrons. So what happens is gradually the ionization energy will increase till the 6th electron, and then there would be a big jump in the ionization energy. So we can start like this. Maybe this is 1, maybe this is 2, 3 here, 4 might be here. Here can we draw 5, and here let's say is 6. But 7th would be here, 8th would be here. Why this happens? Because see, as you remove electrons, what happens is the ionization energy increases. Because now the repulsive force between the electrons decreases, while the attractive force by the nucleus remains constant on the on the electron. After the sixth electron is removed, what happens is you have an octet, and we know removing electrons from octet, it requires a huge amount of energy. That's why we can notice such a big jump between the 6th and the 7th electron. Okay, so let's move to part D. Iron to sulfide, FeS is ionically bonded. Now we have to describe the bonding in this type of solid. So we can first say that the compound is formed by, they're formed by two ions, right? That is the Fe2 plus ion and S2 minus ions. Now, the bond between them, or basically any ionic bond, is basically the electrostatic force of attraction between these two ions. So yeah, we can just write it here. The bond is electrostatic force of attraction. There's the first point, there's the second point. Now, the second question here says, state a technique that could be used to determine the crystal structure of solid compound. So the general technique which we employ to determine crystal structures of solid compounds is X-ray crystallography, and that will be the answer here. Now in this third part, we have to write the full electronic configuration of sulfide ion. So sulfide ion is basically S2 minus ion. Okay. So sulfur has a total of 16 electrons because its atomic number is 16. S2 minus is 2 extra electrons. So the total number of electrons in S2 minus is 18. So we have to write the full electronic configuration here. So 1s2, 2s2, 2p6, 3s2, 3p6. And that would be the full electronic structure of S2 minus. Now, in the next question, outline in terms of the electronic structure why ionic radius of sulfide ion is greater than that of the oxide ion. Again, we can do this explanation using electronic configuration. So the electronic configuration of S2 minus would be 1s2, 2s2, 2p6, 3s2, 3p6, as we did in the previous question. Electronic configuration of O2 minus would be 1s2, 2s2, 2p6. So we can see that S2 minus ion has an extra shell, that is n equals 3. We know that using the same logic, we say that as we go down a group, the atomic size increases. Okay, so the reasoning would be like this. Has an extra shell of electrons as compared to O2 minus. Hence, it has a bigger size. So the next question says, suggest why chemists find it convenient to classify bonding into ionic, covalent, and metallic. So what happens is any classification makes the job of scientists easier because it helps them, it becomes easy for them now to study the compounds. It also helps them generalize substances, and this generalization meaning like they can say like ionic compounds have high boiling point, while covalent compounds will have a lower boiling point as compared to it. So yeah, we can write the answer in this way. study different compounds, and also to generalize the substances. In this question, it's given that the first step in the extraction of iron from iron 2 sulfide is to roast it in air to form iron 3 oxide and sulfur dioxide. Write the equation of this reaction. So let's try to identify the reactants and products that has been given in the statement. So iron 2 sulfide is FeS and it's generally a solid. It is roasted in air. In air, O2 is the most reactive substance, so obviously it reacts with O2. The products would be Fe2O3, which is iron 3 oxide, it's a solid, and we have SO2 gas. Now we have to balance this reaction. So firstly, we have to balance the iron. If I put a 2 here, it would be balanced. If I put a 2 here, sulfur would be balanced. Now to balance the oxygen, we have 7 oxygen on the right-hand side and 2 on the left-hand side. I can just multiply it with 7 by 2 to balance the oxygen. Now we can multiply both sides with 2 to get whole number coefficient. So 4 FeS solid plus 7 O2 gas gives you twice Fe2O3 solid plus 4 SO2 gas. And this would be the final answer. Okay, so in the next question, we have to deduce the change in oxidation state of sulfur. So sulfur is here in FeS and here in SO2. So initially, oxidation state of sulfur, we would calculate like this. So it's given that Fe is iron 2 sulfide. So oxidation state of iron is +2. And let's say that the oxidation state of sulfur is X. Now FeS is a neutral substance or a neutral compound. So we would equate it to 0. So we get here X equals -2. This is the initial oxidation state of sulfur. Now the final oxidation state, sulfur becomes SO2. So we know that the oxidation state of oxygen is -2. So let's assume +X being the oxidation state of sulfur. And the oxidation state of oxygen is -2. And we have 2 of the oxygen. This will be equal to 0 because SO2 is neutral. So X would become +4. This is the initial oxidation state. This is the final oxidation state. So net change would be final minus initial. So it would be +6. So the next question says, suggest why this process might raise environmental concerns. So in this case, the SO2 gas, which is evolving, would be our main concern because SO2 is generally an acidic oxide. So what happens is when SO2 rises, it would combine with the water vapor in the clouds. And as a result, the rain which would occur would become acidic. So we can write it like this. Produced would result in acid rain, which is harmful for the environment. Now let's move to the final part of this question. Explain why addition of small amounts of carbon to iron makes the metal stronger. So what happens here is when you're adding carbon to iron, you're making an alloy basically. So carbon disrupts the crystal structure of the iron because obviously carbon has a smaller size. If you're introducing a smaller size particle in a crystal of a larger size, obviously the crystal will get distorted. But because of this disruption, what happens is in between these layers of iron, small carbon particles are introduced. So what happens is it produces a hindrance for the layer to slide over each other. As a result, the metal becomes harder. So we can write like this: carbon disrupts the crystal structure of iron as it has a smaller size. So because of this disruption, it becomes difficult for the layers of iron atoms to slide over each other. Okay, so that would be the answer to this question. Now let's move to question 2. It's given that iron 2 sulfide reacts with HCl to form hydrogen sulfide, that is H2S. First part, draw the Lewis structure of hydrogen sulfide. Hydrogen sulfide will look like this, obviously. The sulfur will have 2 lone pair of electrons. Predict the shape of hydrogen sulfide molecule. It would be either bent, you can say bent, or V-shaped. In aqueous solution, hydrogen sulfide acts as an acid. Say the formula of its conjugate base. To write the formula of any conjugate base of an acid, we have to remove an H plus ion from the acid. On removing H plus ion from H2S, it would become HS minus. And that would be the conjugate base of H2S. In the next question, saturated aqueous hydrogen sulfide has a concentration of 0.1 mole per dm³ and pH of 4. Demonstrate whether it's a strong acid or a weak acid. As pH is 4, we can say that the H plus ion concentration is 10 to the power minus 4. Okay. But the H2S concentration is 0.1. So only a very less percent H2S molecules have dissociated. Because if the entire H2S have dissociated, we would have a very low pH. Okay, but here the pH is high. So we can say that a very less number of H2S molecules have dissociated. So it's a weak acid. In the next question, we have to calculate the hydroxide ion concentration and saturated solution of H2S. We know that H plus ion concentration times OH minus concentration would be equal to 10 to the power minus 14. So H plus is 10 to the power minus 4 is given in the previous question. So we have OH minus concentration as 10 to the power minus 10. The unit would be mole per dm cube. Now the last question of this question 2. A gaseous sample of nitrogen contaminated only with hydrogen sulfide was reacted with excess sodium hydroxide solution at constant temperature. Volume of the gas changed from 550 to 525 centimeter cube. Determine the mole percentage of hydrogen sulfide in the sample, stating one assumption you made. Now it's given that in a question, gaseous sample of nitrogen contaminated only with hydrogen sulfide. Now nitrogen is an inert gas. Nitrogen doesn't react with NaOH. H2S gas would react with NaOH to form Na2S, which is a solid, and it will also form water, which is a liquid. So we can say volume of gas that has decreased is basically H2S. Okay, so volume of H2S in initial sample was 550 minus 525, that is 25 centimeter cube. Now we have to use the ideal gas equation in order to get the moles of this H2S and the total moles of the compound. So PvH2S is equal to moles of H2S times RT. Now we would be assuming pressure constant. Although it's just given that the temperature is constant, we would also assume that pressure is constant. So moles of H2S would be P by RT times 25. Okay. Now similarly, if I want to find the total moles, we can just use the ideal gas equation again. So PV total would be equal to N total times RT. So N total would be P by RT times V total, which is 550. Now we know the moles of H2S, we know the total moles, we can find the mole fraction. Would be moles of H2S by total moles. This would be P by RT times 25 divided by P by RT times 550. These will cancel out. So we have times 100 obviously. Okay, we need the mole percentage, not mole fraction. So just edit it out to mole percentage. And yeah, we have to multiply it by 100. So what we get it is 4.545%. This should be the answer to the question. Now what are the assumptions? First assumption is we have assumed N2 and H2S as ideal gases. Ideal gases that we have assumed. And secondly, we have assumed that pressure remains constant throughout the reaction. That's the answer to this question. Now moving on to question 3, in the first part we have to deduce the Fe2 plus and Fe3 plus ion ratio in Fe3O4 or in 1 mole of Fe3O4. To solve this, firstly we need to find the total charge that is on the iron atoms. Okay, so we just can use the normal oxidation number rule. 3x plus 4 times minus 2 will be equal to 0. So you can say x is basically 8 by 3. Okay, or you can say 3 atoms of iron should have total of plus 8 charge. Okay, so in Fe3O4, this 3 iron atoms should add up to a charge of plus 8. Now you can have Fe3 plus and Fe2 plus. Clearly you would need 2 3 plus charges and 1 2 plus charges to create a total charge of plus 8. So the ratio, so you would need 1 Fe2 plus and 2 Fe3 plus. Okay, so the ratio will be 1:2, and this is the correct answer to this question. In the next part, it's given that iron exists as several isotopes. State the type of spectroscopy that could be used to determine the relative abundances. Obviously, we use mass spectroscopy. Moving on to the next question. We have to state the number of proton, neutrons, and electrons in each of the species. Now, obviously, the top one is the mass number, the lower one is the atomic number. Number of protons is always equal to the atomic number. And as it is a neutral atom, the number of electrons will be equal to the number of protons. Number of neutrons will be mass number minus number of protons. So this will be equal to, this will be equal to 28. In the next case, again, this is a charged ion. Okay, so for a charged ion, the number of protons will always be equal to the atomic number. Okay, what happens is it has plus 3 charge. So that means it has 3 electrons less than what it should be at the normal stage. So normally it should be 26, but it has 3 electrons less. So number of electrons is 23. Number of neutrons now would be 56 minus 26, that is 30. So this would be the correct answer to part 2. Now moving on to part C. It says that iron has a relatively small specific heat capacity. The temperature of a 50 gram sample rises by 44 degrees Celsius when it absorbs 1 kilojoule of energy. Determine the specific heat capacity of iron, and we have to use section 1. So what we need to check in section 1 is this formula, basically Q equals MC delta T. So we just have to directly apply this formula and get the value. So Q will be MC delta T. Now check the units is joule, gram inverse, Kelvin inverse. Okay. So delta T, if it's in degrees Celsius, it will also be equal to delta T in Kelvin. Okay, because the scale between Celsius and Kelvin, they have the same markings. Okay. Or you can say they have the same divisions. So Q is 1000 joules. Mass is 50 grams. We need to find out C, and delta T is 44.4 Kelvin. So from here, we get C equals 1000 joule by gram Kelvin divided by 50 times 44.4. Finally, what we get is 0.45 joule gram inverse Kelvin inverse. Okay, that's the final answer to part C. So let's move on to option D. A voltaic cell is set up between Fe2 plus and Fe3 plus and Fe2 plus half cells. Okay, so we have to deduce the equation and cell potential of the spontaneous reaction. Now, it says to use section 24. In section 24, what we are given is we are given the standard electrode potentials. So let's try to figure out Fe2 plus and Fe3 plus from here. Here is our Fe2 plus to Fe, and here is our Fe3 plus to Fe2 plus. Okay, so for a spontaneous reaction, your cell potential should always be greater than 0. Okay, and to find out the cell potential, our general formula is E naught cathode minus E naught anode. So this value should always be positive. Now we can see that if we can keep this one on cathode and this one on anode, our net cell potential will come out as positive. Okay, so firstly, let's calculate the cell potential. Cathode minus E naught anode. So this will be plus 0.77 minus of minus 0.45. Okay, so if we add this two up, we have 1.22 volts, which is positive. So this is the correct answer. Now we have to frame the equations. So at anode, we have oxidation. Okay, so firstly, let's write the cathodic reaction. Cathodic reaction is Fe plus 3 plus electron gives you Fe2 plus. Okay, this is the cathode. In the cathode, you always have reduction, and in the anode, you have oxidation. So anodic reaction, this reaction we have to reverse and write it. So Fe gives you Fe2 plus 2 electrons. Now, to write the net reaction, we have to cancel out all the electrons. So we have to multiply the first reaction with 2. What happens is both the electrons, this will be 2 electrons on the left-hand side and 2 electrons on the right-hand side. They will cancel out, and we will get the final equation. So Fe plus 3 equals plus Fe solid gives you thrice Fe2 plus equals. This is the final cell reaction or cell equation, you can say. That's all about part D. Let's move on to part E. Now, this is pretty simple. This is the normal electrolysis setup. So I know that to the negative charge, the cathode is connected. To the positive charge, anode is connected. Okay. Now we are electroplating iron with zinc. So for this case, what happens? We put iron on the cathode side and zinc on the anode side. Okay. And as we are electroplating iron with zinc, what happens is we have to choose a solution such that it has zinc ions on it, or basically a soluble zinc salt. So I can just write ZnSO4. Okay, equals here, and this will be the correct answer to this question. Moving on to the next question. Unlike typical transition methods, zinc compounds are not colored. This is because zinc, okay, has a zinc or Zn2 plus has a completely filled D shell. Okay, that is the reason it doesn't show any colors. For colors to show, you should have electrons in the D subshell. Or yeah. So for example, anyone having like 3D0 will not show colors, or if you have like a fully filled D orbital. Okay, in this question, we have to outline why, unlike the other transition metals, zinc compounds are not colored. Now, for a compound to be colored, okay, for a transition metal to be colored, the main criteria is it should have unpaired electrons in its D subshell. Okay, but zinc, or you can say Zn2 plus ion, okay, has a completely filled D subshell. So, in two cases, if you have a compound that doesn't have any electrons in the D subshell, or if you have a compound which has a fully filled D subshell, these won't show colors. Okay, so we can just say Zn2 plus has a completely filled, Zn or Zn2 plus has a completely filled D subshell. That's why zinc compounds aren't colored. Now moving on to the next question. Transition metal like iron can form complex ions. This is the bonding between transition metals and their ligands in terms of acid-base theory. Now what happens here is whenever you have a complex compound, the ligands form dative bonds with the central metal ion. Okay, so dative bond means the electrons will come from the ligands and they will kind of form a bond with the metals. Okay, so what happens exactly here? The central metal atom is basically accepting electrons, and by Lewis theory, we can say electron acceptors are called acids. Okay, so yeah, in this case, the metal ion acts as a Lewis acid. So we can just write it out here. Donate electrons to the central metal and forms dative bonds. Hence, central metal ion, or you can say central metal, acts as an electron acceptor. And we know by Lewis theory, electron acceptors are acids. So the central metal acts as an acid. That's the answer to this part G. Now moving on to question 4. We have hydrogen peroxide that can react with methane and oxygen to form methanol. This reaction can occur at 50 degrees if gold nanoparticle catalyst is used. Now, in part A, we have a Maxwell-Boltzmann curve for uncatalyzed reaction. We have to draw a distribution curve at a lower temperature T2 and show on the diagram how addition of catalyst enables the reaction to take place more rapidly at T1. So what happens is, as we are trying to draw the curve at a lower temperature T2, what happens is at lower the probability of energy or the probability of atoms having this much amount of energy will be shifted to the left. So it will somehow look like this. Let's try to draw this. And yeah, as you're lowering the temperature, the probability of particles having this much energy will be the highest. It will shift to the left. Now, we also need to show how addition of catalyst will enable the reaction to take place more rapidly than at T1. So at T1, your activation energy is here. Now, when you add a catalyst, what happens is this activation energy will decrease. As it will decrease, so this EA will shift on the left-hand side. So I can say somewhere around here will be your EA. And these much molecules are available for reaction. Okay, so that is all about part A. Now part B. Hydrogen peroxide could cause further oxidation of methanol, suggest a possible oxidation product. So for methanol, there can be two oxidation products. One of them is methanoic acid or another one is methanol. So this one is methanoic acid. Methanol is this. This is methanoic acid and this one is methanol. So the answer should be methanoic acid and methanol. Now, in the next question, we have to, it's given that methanol is usually manufactured from methane in two-stage processes. Okay, so you have two reactions, and these are the two steps for formation of methanol from methane. Now we have to find the overall equation. How to find the overall equation? We just have to add these two equations and cancel anything that's common on both the sides. Okay, while adding this, adding these two reactions, we will get this initially. Twice H2, and the right-hand side would be CO plus twice H2 plus CH3OH. Now we have to cancel the common stuff. This is common here. You have 2H2 here, you have 3H2, so it will just become H2. The final reaction will look like this, and you have to mention the states, obviously. You will have H2 gas plus CH3OH liquid. This is the final answer. Now, it says that 8 gram of methane is completely converted to methanol. Calculate 3 significant figures, the final volume of hydrogen at STP in decimeter cube. And we have to use section 2 and section 6 of the data booklet. So, firstly, let's write this equation. Now it says completely converted. So the reaction will look something like this. The arrow will be a one-way arrow. CH3OH liquid. Okay. Now, we are given 8 gram of methane is completely converted to methanol. So firstly, let's find the moles of methane. Now, this question specifically says we have to use section 2 and section 6. So in section 2, you just have to get this formula. Okay, not this one. Yeah, molar volume of ideal gas at STP is 22.7 decimeter cube per mole inverse. And section 6 gives you the periodic table. Whenever they say use section 6, you have to use the specific values of the mass numbers. Okay, to calculate the molecular weight. So in this case, I'll be using it. So the molar mass will be carbon has 12.01 and 4 hydrogen will have 4.04. The total will be 16.05. Sorry for that. So 8 divided by 16.05, this would be 0.498. Now we have to apply stoichiometry to get the moles of methanol. So moles of methanol divided by moles of, oh no, we have to find the moles of hydrogen, sorry. So let me just correct it. Moles of H2 by moles of CH4 would be 1 by 1 because the stoichiometry here is 1, here is 1. So the stoichiometric ratio will be 1 by 1. So moles of H2 will be equal to moles of CH4 and that will be equal to 0.492. Now volume of H2. This would be moles. This is 498, sorry. Yeah. So this will be moles times the specific volume at that temperature. So molar volume at ideal gas is 22.7. So we have to just multiply it with 22.7. And we will get the correct answer. That will come out as 11.3 if you write it in significant figures, in 3 significant figures. Yeah. And the unit will be dm cube. That's all about this question. Let's move on to the next one. Yeah. In this next question, we have to find the enthalpy change and we have to use section 11 of the data booklet. Section 11 gives you the idea of the bond enthalpies. So let's start. For these questions, what we need to do is the delta H would be summation of bonds broken. Bonds formed. Okay, because for breaking a bond, it absorbs energy. For forming a bond, it releases energy. Okay, so which bonds are broken? I can see 4 CH bonds are broken, 4 of CH bonds, and I can see 2 OH bonds broken. And which bonds are formed? I can see 1 C double bond O is formed and I can see 3 HH bonds are formed. Okay. Now we have to find the CHO, these bond enthalpies. So CH bond enthalpy, CH bond enthalpy is 414. So 4 times 414. OH bond enthalpy is, this is O, this is H, this is 463. So 2 times 463. My C double bond is given here 1077 minus 3 times HH bond enthalpy. H is here, H is 436. 436. Finally, after doing the calculations, what we have is plus 197 kilojoule per mole. Or we can just write kilojoule. It's okay. This will be delta H. And this will be the final answer to this question. Now, what happens is delta is that we have calculated here is actually different from the delta H of value that's given in section 12. Why is the answer different? Because these bond enthalpies that are there in section 11, these are average bond enthalpies from all the compounds they could possibly find. Okay, so that is not specific to a compound; it's an average value. But section 12 gives you specific values of the enthalpies of formation. That's why you will always find a difference. So bond energies are average values and not specific to a compound. That's all about this question. Let's move to the next. State the expression of Kc for this stage of the reaction. So we have to write Kc for this equation. This is probably very easy. Firstly, we have to take the product side, H2 whole cube times CO. We have to divide it with H2O and CH4. And that's the correct answer to this question. Now this reaction, so this reaction, what happens, has an enthalpy which is positive. Positive enthalpy means system is absorbing heat or the reaction is endothermic. Okay. So when you increase the temperature of an endothermic reaction, what happens? The reaction gets shifted to the forward direction or the value of Kc increases. So I can say Kc increases and the reaction is shifted to the forward direction. Now moving on to part D. We have this equation of formation of methanol, that is the second stage. Now this equilibrium constant Kc has a value of 1.01 as 298 Kelvin. We need the delta G naught value at this temperature. Okay, and we have to use section 1 and section 2. Again, it has section 1 and section 2. In section 1, you have to pick out this equation. Delta G equals minus RT ln Kc, because this gives you the relationship between delta G and Kc. Okay, and from this 2, you just have to take this universal gas constant value. So delta G naught is equal to minus RT ln Kc. 8.314, temperature is 298 Kelvin, and ln 1.01. So upon solving this, what we get is minus 24.6 kilo. This will be joule per mole, because on the value of R, you see the unit is in joule. In the next question, we have to calculate the delta S naught. Again, we have to use the section 1. In this part, we have to use this equation, delta G equals delta H minus T delta S. So delta D we have calculated as minus 24.6. Delta H is in kilojoule. So we have to convert it to joules. Or what we can do is we can convert delta G to kilojoules. I guess that would be better. Temperature is 298 and this would be delta S. Upon solving this, what you get delta S is as minus 0.433 kilojoule per mole Kelvin. And also you can write it as minus 433 joule per mole Kelvin. That is also the correct answer. It's delta S naught. Okay, so we are done with this. Now we have to justify the sign of delta S with reference to the equation. Delta S, we found that the delta S is coming as negative. Why is the delta S coming negative? Delta S negative means randomness is decreasing in the system. Okay, see, that's actually correct, because you have 3 gaseous moles on the left hand side and only liquid moles and only 1 mole of ethanol on the right hand side, which is actually a liquid. So what happens is your final product is a liquid while your reactants are gas. Obviously gases are more random. So when it gets converted to a liquid, your randomness falls, and that's why delta S is negative. So we can write the answer like this, as the reactants are gaseous while the product is a liquid. So randomness of the system decreases and delta S becomes negative. Negative. That's the answer to this question. Now we have to predict how temperature change would affect the spontaneity of the reaction. Now see, we are decreasing the temperature. And this reaction is an exothermic reaction. So on decreasing the temperature of an exothermic reaction, what happens is your reaction will shift to the forward direction. So as the reaction will shift to the forward direction, we can see that the value of delta G will become more negative, okay, and the reaction will become more spontaneous. You can also prove it by the formula. So let's write this now. As the reaction is exothermic, decreasing temperature will shift it to the forward direction and make it more spontaneous. Now, how to prove this by using equations? So delta G would be minus RT ln Kc. Now, what happens is if you decrease temperature, the overall value of Kc will increase. Okay, so this term, this negative term will increase. So what happens is delta G will become more negative. Okay, so delta G will be more negative, and as a result, the reaction will be more spontaneous. Now let's move on to the next question. This is question 5. Ethanol is obtained by hydration of ethene. Set the class of compounds to which ethene belongs. Obviously, it will be alkene. Okay. Molecular formula of next member to the homologous series to which ethene belongs is obviously ethene, and it will come as propene. So propene, the molecular formula is that will be C3H6. Now we have to justify why ethene has only one single signal in its H1 NMR spectrum. This is because if you check the structure of ethene, it has this plane of symmetry. So what happens is due to this plane of symmetry, all the hydrogens become equivalent, and that's the reason it has only one single signal in its NMR spectrum. Equivalent, and only one signal is generated. That's the answer to this question. Let's move on to the next part. Deduce the chemical shift of this signal using section 27. So obviously you have a double bond here. So this is section 27. I can see double bond here, and this can be any group here. I can just add an H here. So it would be between 4.5 to 6.0. So the chemical shift will be 4.5 to 6.0. State the two possible products of incomplete combustion of ethene that would not be formed by complete combustion. So it says that would not be formed. So CO2 and H2O won't be the answer. The two incomplete combustion products are CO, that is carbon monoxide, and carbon, that is called soot. So yeah, that's the answer to part C. Moving on to part D. A white solid is formed when ethene is subjected to high pressure. Deduce the type of reaction that occurred. So see, we are not putting any reagent, we are just subjecting it to a high pressure. Okay, and a solid is getting formed. Obviously, this type of reaction is a polymerization reaction, and where polyethene is getting formed. This will be a polymerization reaction. Now in part E, we have to stress the mechanism for the reaction of propene with hydrogen bromide using curly arrows. Okay, let's try to solve this. This would be step 1. This would be propene. So this is the propene molecule. This is the high electron density double bond, and you would have HBr. In HBr, Br is more electronegative than hydrogen. So Br will have a little negative charge on it. Hydrogen will have a little positive charge on it. Okay. What happens is this double bond will attack this positively charged hydrogen, because double bond, it is a high electron density area. When this HBr comes close to it, what happens is as H is slightly positively charged, this double bond will attack on this H and kick out this bromine. So with this, we can actually have two carbocations. Okay. This is the first one, and this is the second one. Okay, so let's number it as 1 and then number it as 2. Now step 2 is bromine will get attached to both of them. Plus Br minus Pr, this will be the major product. And the minor product will be formed from the second one. That would be so we just have to connect the Br to this positive charge, and we will get the final product here. This will be your minor product. This is the complete mechanism and answer to part 1. Now in part 2, we have to explain why the major organic compound is 2-bromopropane and not 1-bromopropane. Here this is 1-bromopropane, and this is 2-bromopropane. Okay, now we have to explain why 2-bromopropane is a major product and 1. This is because these carbocations, okay, which are formed after step 1, we have to check the relative stability of these carbocations. The one which is more stable, that will yield the major product. Okay, so for a stability check between 1 and 2, we can see that 1 is more stable as the positive charge is surrounded by 2 methyl groups. Okay, because here is one methyl group and here is another methyl group which is directly surrounding the positive charge. But in this case, only one group, or you can say an ethyl group, is just surrounding it. So obviously, in this case, the charge will be lower. In this case, the charge will be little higher. And we know that lower the charge, the more stable is the system. The positive charge is surrounded by 2 methyl groups, while in 2, it's only surrounded by 1 ethyl group. Hence, 2-bromopropane is the major product. That should be the answer to part 2. Now, 2-bromopropane can be directly converted to propan-2-ol. Identify the reagent required. You can just use SN1 or SN2 reactions. So any compound that gives OH minus sign will be our answer. So the answer can be either NaOH, it can also be KOH. So in part 4, it said that propan-2-ol can be formed in one step from a compound containing a carbonyl group. State the name of this compound and type of reaction that occurs. Now, carbonyl group means a ketone or an aldehyde. So propan-2-ol is a 2-degree alcohol, and we know that only a ketone can, on reduction, on reduction will give you a secondary alcohol. Okay, so the ketone will be this. If you put a reducing agent, you will get this alcohol. So what's the name of this carbonyl compound? It is propanol. Okay, propan-2-ol. So the name of this carbonyl compound will be propanon. And the reaction will be reduction reaction. Now moving on to question 6. You have nitrogen pentoxide N2O5, which is treated in a colorless gas that undergoes thermal decomposition to produce brown nitrogen gas. How can we measure the extent of decomposition? Now, thing is, see, on the left hand side you have 1 gaseous moles, and on the right hand side you have 2.5 gaseous moles. So what happens is 1 gaseous mole is changed to 2.5 gaseous moles. As a result, what happens is as the reaction progresses, the volume of gases produced will increase. As the volume increases, obviously there would be the pressure inside the vessel will increase. Okay, so you can just mention 2 points. Will increase. As a result, pressure will also increase. Now here is the data for decomposition at constant temperature, which is given. Now for this one, you have to plot the missing point and draw the best fit line. I've already drawn this. So this is your missing point. That is this point. You have to plot. You can just find 24.3 on the x-axis on this x-axis and 0.71 on the y-axis, and then draw this point, and then you have to draw the best fit curve. You can draw it using a ruler. So yeah, in this case, I use some tools here, but whatever. If you just use a ruler, you will get somehow a line like this. Okay. Now you have to outline while increasing the concentration of N2O5 increases the rate of reaction. Now, if we increase the concentration of N2O5, what happens? The number of molecules will increase. If the number of molecules increases, what happens is the number of effective collisions between these molecules will increase. As a result, products will be formed faster. So on increasing the concentration of N2O5, the number of molecules increases. Hence, the number of effective collisions will also increase, and hence products will be formed faster. Now we have to write the rate expression. As you can see, it's a linear plot between rate and N2O5, which passes through 0. I can write rate is K times the concentration of N2O5, and that is correct. Now we have to calculate the value of rate constant K given its unit. Now how to find this rate constant K? The slope of this line will give you rate constant K. Now what you need to do is you need to find 2 points as I've marked it here, and find the slope between these 2 points. Okay, so this will be delta y by delta x. This will be K. So I've chosen this point. This is the first point. Okay, so y is 0.44, x is 15. So 0.44 is 15 minus. There's the second point, x is probably 2 and y is 0.06. X is 2. So this becomes 0.38 by 13. This would be approximately equal to 0.03. And as this is a first order reaction, okay, and here you see the unit minute. So the unit of the rate constant will be minute inverse. That's all. If you just write this, we'll get full marks for this question. Moving on to question 7, we have oxygen that has 2 allotropes, O2 and O3. We need to draw the Lewis structure for ozone. For ozone, this is the Lewis structure. You have to write or draw all the electrons. So here it's already 3 bonds. So okay, so this is the answer. You can also draw the other equivalent structure, which looks like this. So what is the relative length of 2 OO bonds in ozone? So the answer is both the bonds are equal in length due to the delocalizations of electrons. Both the OO bonds are equivalent because of the delocalization of electrons. Or we can also say delocalization of pi electrons, because technically the pi bonds is shifting between here and here. Now in the next case, explain why there are frequencies of UV light that will dissociate O3 but not O2. Now see, in O2 you have a double bond, okay, but in O3 technically your bond order is not 2, it's 1.5. Okay, it's in between a double bond and a single bond because of this delocalization. I can just mark it in the middle and I can say that its bond order is 1.5. So what happens is lower frequency UV lights has enough energy to break this O3 bond, but not the double bond of O2. So O2, I can write it like this. While O3 has 1.5 bonds, which is weaker than double bonds. Hence, UV light with low frequencies can break the bond in O3 molecules, but not in O2 molecules. Explain using the equations how presence of CCl2F2 results in a chain reaction that decreases the concentration of ozone. Now, this is just a set of reactions. It's given in most of the textbooks. So, if you have CCl2F2 and if you put UV light on it, what happens is you have CClF2 radical. Obviously, this is gas, and you will have Cl radical. Okay. Now, the Cl radical will attack an ozone molecule and form this ClO radical and O2 gas. This ClO radical will further attack an ozone molecule. Okay. And what happens now is you will get the Cl radical and you will get two oxygen molecules, two O2 molecules. So now what happens? The Cl radical is regenerated. So this, let's say this is step 1, this is step 2, this is step 3. Now as the Cl radical is regenerated, it can again attack an O3 molecule like in step 3 and form this ClO radical and an oxygen molecule. The ClO radical will again attack another O3 to form this chlorine radical and two oxygen molecules. So in this way, it can form this chain reaction which will keep going on and on. Now, moving on to our last question. We have propanoic acid, which is a weak acid. So, we have to find the pH of 0.001 mole per dm cube propanoic acid solution using section 21 of the data booklet. Section 21 gives you the pKa values. Okay. So, Ka of propanoic acid, it's here, is 10 to the power minus 4.87. Now, let's write the reaction or the dissociation reaction or the dissociation equation. CS3COO minus. Not CCCO minus, I just missed a CH2. Now we can write the Ka equation. This will be H plus CS3 CH2 COO minus divided by CS3 CH2 COOH. Now we know that this H plus ion concentration will be equal to the CH3 CH2 COO minus concentration, because when one molecule of this propanoic acid dissociates, one molecule of H plus and one molecule of CH3 CH2 COO minus, or the propanoate ion, is getting generated. So obviously these two concentrations will be equal. So plugging in the values, we will get H plus concentration as 1.16 times 10 to the power minus 4. So from here we can calculate the pH, that is minus of log H plus, as 3.94. And that will be the correct answer to this question. Now this is the last question. We have to draw the general shape of variation of pH when 50 centimeter cube of 0.01 mole per dm cube NaOH is added to 25 centimeter cube of 0.001 CaCOOH. Now we have to make some observations here. For example, the initial pH will start with 3.94, as initially you have 25 centimeter cube of 0.001 mole per dm cube of propanoic acid. So initial pH will be equal to 3.94, or you can also write it as 4. What happens at the final pH? See, finally what happens is you have 25 centimeter cube of propanoic acid and 50 centimeter cube of NaOH. So finally what happens is only NaOH will be present in the solution. So as NaOH is a strong base, the POH will be 10 to the power minus this concentration, this 10 to the power minus 3, and pH, I mean not POH, this is the OH minus concentration. So from here the H plus concentration will be 10 to the power minus 11. So pH will be 11. So the final pH will be 11 and the initial pH will be 4. So I can say that it will start from here and finally it will end here, 11, 12, 13, 14. Yeah. Now see, this is a weak acid strong base titration. So we will have an S-shaped curve. Okay. Now where is the equivalence point? Equivalence point will be at 25 centimeter cube. Okay. Because obviously both of them have the same concentration. So 25 centimeter cube of NaOH will completely you can say completely neutralize all of the acid. Okay, so equivalence point is at 25 centimeter cube. What's the pH as equivalent? It is the salt which is formed. It is a salt of weak acid strong base. So pH will be greater than 7 at this equivalence point from salt hydrolysis. Okay, so pH greater than 7 at equivalence point. Another thing is at half equivalence point, what happens is the pH is equal to pKa. So the pKa is how much? 4.87 or approximately 5. So we can say at half 12.5 centimeter cube, which is the half equivalence point, pH will be equal to 5. Okay. Now with all these details, we have to draw the curve. 1, 2, 3, 4, 22, 24, 26, 20. So somewhere here, your curve, let's try to draw this. Like, let me draw a small line here first. Approximately, you can say the lag will be here. Let's try to draw it now. Okay, let's see if all our conditions have met or not. With this part part. Okay, so here is the equivalence point approximately. pH is greater than 7 mostly. Yeah, that is correct. At half equivalence point 12.5. This is 12.5. The pH is approximately 5. So what? So yeah, it's somewhere at around 5 only. Okay, so this is correct. So we can just remove these dots which I made. So yeah, this will be the curve, and this is the correct answer to this question. With this, we end the solutions of this HL paper 2 of time zone 1. I'll soon be posting the time zone 2 paper 1. You can expect the solutions to be ready within the next 3 days. Thank you so much for watching the video. Stay here. Please subscribe to our channel and like this video. Thank you so much again. Goodbye.